Okay, so let's do some recap. Okay, so let's a bit of recap on what we have discussed last lecture. Application of Ampere's law. So first demonstrated if the line is infinite, and this always provide a condition if the line is infinite for a current that passes through an infinite length. So this always provide features for symmetry, and if it's symmetry, similar as what we have done for Gaussian application of Gauss law, so we can apply Ampere's law. So instead of a closed surface, we will apply a closed path surrounding the current, and that determines the direction of the magnetic field. So another example for infinite sheets of current. So saying that let's say the current is directed towards the y direction, and surface current, the unit is ampere per meter, and therefore when we apply Gaussian surface, when we apply Ampere's path, so which is a rectangle, which is a rectangle. So as I explained, that for this rectangle will be the same if we move this rectangle position. If we move this rectangle position to here or to here, okay, the point of observation is the same because it is infinite. So of course the term infinite is relative due to the point of observation. If the point of observation is close to the surface and which is relatively small compared to the dimension of the surface current density, the sheets, then Ampere's law holds. Then we can apply Ampere's. That means when I say the Ampere's law holds, that means it is applicable, is valid. So therefore, this Ampere's path, this rectangular path, regardless where you position this, uh, it always is always true. Yeah, it always holds the theory. And then I have mentioned that, and how do we evaluate the direction of the electric field? I did mention using right hand rule. Okay, so I said that if you use right hand rule, so the magnetic field above and the magnetic field below will be pointing, one will be pointing in the positive x direction, and below the surface, below the current sheets, the magnetic field will be pointing in the negative direction. So there is no magnetic field there's no vertical magnetic field in this case. So there's no direction in the vertical direction. That means no z direction. There's no magnetic field in the z direction. And the evaluation, so the evaluation is basically is half of the magnetic field is basically half of the uh, surface current density. So of course, if we want to include the direction, then we have to make a cross product. We have to make a cross product with the normal direction of the surface. So this is the normal direction of the surface. So the magnitude is basically half of the amplitude of this. If this is a unit vector, then 1 times anything, 1 times a unit is always a unit. So basically, we can say the magnetic field is half of the surface current density. I'm saying the magnitude, yeah. So if we want to look at the direction, then we have to do the cross product. Okay, let's say now another example. So we are going to evaluate the magnetic field in all region, yeah. So the conductor is concentric with each other. So one is carrying a current I. The inner conductor. So the inner conductor carry current I. Outer conductor carry current negative I. Okay. So outer conductor carries current negative I, inner conductor carry current I. And both conductors uh, are concentric. So both conductor is concentric. So both conductor is concentric. That means they are in the center. They are they are aligned in the same XL direction. So they have the same center here. Both conductors are concentric. Okay. So here we is provided that the z direction, that means this is positive z direction. So the current direction, the inner current direction that carries by the inner conductor, it is pointing towards the positive z direction. And and the outer conductor carries the current in the negative z direction. Okay, because it's negative current. So this negative here means one is out from the page, which is the negative, which is the positive z direction. One is into the page, which is the negative z direction. This is what it means. So the outer conductor, even though it is a spherical, is a cylindrical shell. So it's a cylindrical shell that have a thickness t. That have a thickness t. So now, so we are going to determine the magnetic field everywhere. So we have to determine first the magnetic field. So we have to determine the magnetic field everywhere. So first, I will determine R less than A. Yeah. I will determine R less than A. So based on Ampere's law, So the charge enclosed, so the I enclosed, the current enclosed is equals to the path, the closed path. Yeah. So on my left hand side, so if I okay, so the red dot, I mean the dashed line represent the Ampere's path. So this is my I would say this is my Amperian path. Amperian path. Yeah. So the radius is A. Uh, uh, the inner one is A. So sorry, I mean this represent the inner conductor. That's why I say the radius is A, while the Amperian path, the radius is R. Okay, is R. Okay. So on my so the charge density then, so is so let's say charge density is uh, J. So on my left hand side will be H 2 pi R, right? So what about this now? So this will be the surface. I mean the current. I mean this will be the enclosed surface whereby the current flow through. I mean this surface here, the one that I'm shading. So that's the current density. But the overall current density, the overall J current density is basically I divided by pi a square. Integrate with ds. So this surface here will be no need integrate. So this surface here will be pi r squared, right? So therefore, the magnetic field is then I divided by r 2 pi a square in the phi cap direction. Okay, in the phi cap direction. So this way here. So the in the phi cap direction. So while now I will evaluate now outside between B and A. Yeah. Okay. So the current enclosed, similar. On my right hand side will be 2 pi r. Okay. So now the current enclosed will be, if let's say go back to our diagram here. So if I'm enclosing the entire conductor, so which is this part here, then so which is this part here, entire conductor. Okay. So I'm enclosing the entire inner conductor. So therefore, that is uh, the the overall current that carries by this conductor, which is I. So therefore, uh, the I enclosed will then be I. So which is I equals to H 2 pi R, and therefore the magnetic field is I divided by 2 pi R cap. Okay. Right now. So what about in between now? Okay. Uh, so I will say now. So I will evaluate now between R, B plus T, and B. Yeah. Greater than B, lesser than B plus T. Yeah. So in this region, in the inner conductor region. Sorry, in the outer conductor region. So I'm going to enclose. Maybe I will just copy and paste this diagram. Okay. So now I'm going to find out what is the magnetic field inside this region here, the one that I'm shading. So the outer conductor. So what is the magnetic field in this region, in the shaded region? So the expression never change. Is only the limit, and we have to take into account of two things. So if I'm going to define my if I'm going to define my Ampere's path that lies that my Ampere's path that lies in this region. Okay, the Ampere's path that lies on in this region. Okay, so what would be the current enclosed in this case. So what I'm saying is, if let's say if let's say my Ampere's path, so my circle is not going to be a nice one. So what I'm saying is, if my Ampere's path enclosing, which lies inside within this conductor region, so what would be the current enclosed in this case? So from here, we can see that it is this Ampere's path here, the one that, if you can see from what I draw here, that means this Ampere's path enclosing the inner conductor, right? So the inner conductor carries a current I, okay? So my current enclosed will be I, so there's 1. And also partially, so let's say my Ampere's path, my Amperian circle is R, yeah, okay, within within which is within the outer conductor, within the thickness of the outer conductor. So it's going to be what now? Minus, okay, current density ds, okay. So there is no, so the thickness of that. So let's say, what will be the thickness now? So let's see. I will copy this diagram again so that you can have a visualization. Two pi r. 2 pi r is, I mean, I think you get the idea, Muhammad Adin. Just that, is it 2 pi r or pi r squared actually? Yep. So, okay. So here is the thickness. Okay. Here is the thickness T. So we have a thickness T and the outer radius. Sorry, the outer radius, which is B here. So this diagram I've exclude. I mean, for this diagram that I'm drawing, I have excluded the inner one. So this is B, yeah. So I'm just drawing this. So I'm just drawing the outer one now. I'm just drawing the outer one. So this is a thickness T, okay, as mentioned in, I mean, as illustrated in the figure. So the outer one is B, and therefore, if let's say my Ampere's path lies between this region, so I can write it that this is negative. So that the negative sign is due to the current direction, yeah, the current direction, negative I pi B plus T whole thing squared minus B squared. Yeah. So that's the current density. And here will be multiply with dot ds. So I integrate the area that covers from where? From B to R, right? Is it B to R? Maybe I just write again. So I'm just writing down the current enclosed by the Ampere's path. So this is minus I. Oops, sorry. Ish. Sorry about that. Sorry about that. Thickness T, sorry about that just now. So I will write down back the parameter. So this B. So the current I mean, following the Ampere's path that I draw here, so the current will be the enclosed current will be I. So the current density is I divided by pi B plus T square minus pi B square, right? And if let's say, so it will be, let's say 4 pi R, okay? R squared, okay? So the limit will be B to R, right? The limit will be B to R, right? So the integration of this, the integration, I mean, so let's say now, so my Ampere's path cover like this, right? If my Ampere's path cover like this, so that means there's a certain region that enclose. So this region here, so here to this, I mean from the center to the Ampere's path is R, while the outer, I mean the outer conductor is B. So the area enclosed is 4 pi R squared. From the limit is from B to R, right? Okay. And okay, first I want you to understand this part first. Do you understand how I get this? First of all, so I'm talking about, let's say we are defining the Ampere's path, which I already shown here. I mean this part here. First, I want you to understand that the red line, which represent the Ampere's path. So the current density, So the current density is current divided by the entire area, the entire area of the thickness, right? So this is pi b plus t squared minus pi b squared. So does this make sense to you? What about others? So does this make sense to you? I mean, everyone, this part here. So the current density J, it is the current, the outer conductor, which is carrying a current negative I. So therefore, there's a negative sign here. So current density is current divided by area, right? So the total area of the outer conductor is the thickness T, right? So the area is pi b plus t square minus pi b square. Does this make sense to you? Is the rest following or not? Beside Muhammad Adin and Jen Y. Does this make sense? I mean, is everyone following? I mean, this is important for you. Look, I hope you are following, because next week will be your test. You already know, all right? Um, some of you still need to attain a certain percentage for make good, at least. Yeah. If you are below 40, if you achieve 38 to 39 marks overall, I still can push you to 40, and then you can have a make good assignment. But if you are below 40, like 30 to 35 marks, I can't help you. All right. So please make sure you understand, you at least please make sure you understand what I'm trying to tell you here. Okay, so moving on. Um, so this is equals to the enclosed, yeah, the current enclosed. So therefore, the current enclosed, so this will be pi 2 2bt plus t squared. Yep. And here will be 4 pi Okay, so this is charge enclosed, which represent on the left hand side, and the right hand side, the magnetic field. So using Ampere's law, so therefore the magnetic field inside here will then be I. So the whole thing divided by 2 pi r. Yep. So r cap. Of course, we can further simplify this. We can further simplify this. Yeah. So this will be I 2 pi r minus I r squared minus b squared 2 pi r so the whole thing is in the radial direction. Okay. So this is 2I, yeah. Okay. And lastly, the region outside, so which is r greater than b. So the region outside, the charge enclosed is I minus I. Okay, so which is equals to 0, and therefore for magnetic field outside is equals to 0 as well. So there's no magnetic field outside, because since they are concentric, since this is concentric, so if I define the Ampere path enclosing the entire structure, okay, so one is positive I, one is negative I, so they cancel off each other, and therefore there's no magnetic field. Yeah, there's no magnetic field. Okay, so that's about it. Okay, so yeah, r cap. Oh, sorry, it's not r. Yeah. Sorry, I think it's not r cap. It's phi cap. Sorry. Because it's circulating. Yeah, circulating phi cap. Okay, so let's look at one example here. All right, planes z equals to 0 and z equals to 4 carries a current K equals to in the negative x direction and positive x direction respectively. So determine the magnetic field at these 2 points. So let's draw this. So one is at on the xy plane at the z equals to 0 plane. So the current direction is here in the negative x direction with the magnitude of -10 x cap. And another one which is above it in the, so at z equals to 4 plane, so that is pointing 10 x cap. Okay, so this region here is at z equals to 4, and this region here is z equals to 0. Okay. Okay, first the region is 111, right? So the region is 111. So 111 is in between it is in between the 2 planes, right? It is in between the 2 planes that carries the current. Okay, so let's evaluate this. So let's say for the magnetic field contributed by the current that is pointing at the negative x direction. So let's say I make it as 1. Okay, h1. So at this point here, okay, which is in between, so it is above. So for this point, it is above this plane. It is above z equals to 0 plane, and therefore it is half k times n cap. So cross n cap, which is z cap, right? -10 x cap cross z cap. So x crosses z is -y. So, but this, if it's a negative here, so it's 5 positive y cap, right? Okay. For H2 is the contribution by -10x, positive 10x. So again, I have half 10x cap so the direction now, so the plane direction, so if for this plane direction, the normal direction is in -z for this plane here. For this plane here is in -z, so cross -z cap. So again, I have 5 y cap. So therefore, so at this point, therefore is h1. So the magnetic field, the net magnetic field is 10 y cap. So for part B here, it is a, so everything is above, yeah, it's above 0, -3, 10. That means this point is above z equals to 4, and also z equals to 0. So it's above this point here. Okay. So then, okay, before I move on, do you know why I said this is negative z direction? So, I mean, how do I determine the direction here? So positive z. So as I said, this is in between the two planes. 111, it is in between the two planes. So let's say this is 111. So the from the plane to here, from the plane to here, it is in the positive z direction, right? So it's, I mean, from the direction of the plane, from plane measure to, I mean, from the plane measure to the point of interest 111, it is pointing in the z direction. While on the other hand, z equals to 4, from the plane measure to the point of interest, it is pointing in a negative z direction. So that's therefore I get negative z. So if we look at the definition, we go back to the definition of that. You say normal unit vector directed from the current sheets to the point of interest. From the current sheet, that means from the plane to the point of interest. Okay, so therefore I have therefore how this is how we determine the normal direction. So while on the other hand for B, so again H1 is half negative 10 x cap crosses z cap equals to 5 y cap, but H2, so H1 is half and negative 10 x cap crosses positive z cap, so it is 5 y cap. While H2 10 x cap, so now the position now is above uh, plane z equals to 4 and also z equals to 0. So the direction from the sheets to the point of interest, it is pointing in the positive z direction, right? So this is negative 5 y cap. So x cap crosses z cap. X cap crosses z cap, it is pointing in the negative y direction. And therefore, H net, the net magnetic field, is going to be 0. Okay, so that's about it for example 3. So now example 4. So we have a toroid dimension, excuse me. So, excuse me. So we have a toroid. So we have a dimension of, so the toroid cross section is uh, the toric. This is the toric cross section. So the area here is so the height from here to here. So the diameter of this is 2a, and therefore the radius of this is a, right? So it's pi a squared. So this is the area. So we want to determine what is the magnetic field inside and outside the toroid. Okay. So the dotted lines, represent the ampere. Let's say the dotted lines shown in the diagram. It represent the Amperian path, right? Okay. So imagine now the current is coming from here, right? This is the current direction. So here is going in, right? So this is going in, going in, going in, right? Going in. And here is going out. So, sorry, going in is not dot, it's a cross, sorry. Going in is a cross here, sorry. So into the page, it is cross, sorry. And at this point here is going out from the page, right? Out from the page. Okay. So I won't draw. I won't continue the rest. So this is for illustration. So for each of this winding, that go in, that wrapping around the toroid. So the wire that into here into the page. Okay. If there are n windings, that means you wind n times. You wind n, you wrap the toroid n times, n turns. So the Ampere path so the Ampere's path enclose how many current? So enclose how many current? So by Ampere's path, so we can say by Ampere's law. So enclose how many current? How many current element are there? So the I enclose is equals to H times 2 pi R, 2 pi rho, I would say. So this is rho, 2 pi rho. Okay. So there's the radius unit. It's the radius symbol for rho or R. Okay. So how many enclosed current? If let's say this is my current, the current magnitude is I. So how many enclosed current here in this case? If I have n windings, that means I have n of these points, right? I have n of this current that go into the page. I have n of this current that goes into the page. That means this is n times I. So in the phi direction. Okay. So this is inside the toroid, yeah. So this is inside the toroid. So I would say this is negative phi here, in the negative phi direction. Okay, uh, because it is clockwise. So if it's anti-clockwise, then this is a positive phi. Okay, so this is the magnitude of n times I divided by 2 pi rho. It is the magnetic field inside the toroid. So what about outside? So now if I define the Amperian path enclosing the entire toroid, so I have the same amount of current into the pitch and out from the pitch, right? If let's say we wind, so the same amount of current that goes into the pitch and also come out from the pitch, the same amount of in and out. So therefore outside is 0. So the application of Ampere's law in this case, it is feasible due to the fact that the current distribution is symmetrical, because uh, if I apply this Ampere's path, so if I imagine if you walk along this path here, you walk along this path here, that I have n turns. I have n turns. That means in anywhere I walk along this path, so anywhere I walk along this path will be the distribution, the current distribution will be the same. So therefore it is feasible. And same goes for the outer region outside the toroid. Again, the current distribution is symmetrical. So therefore the circular path, it is appropriate. It is appropriate for this situation. Okay, so yeah. So this is the solution for this example. Okay. So magnetic flux density. So it's the same as what we discussed for electric flux, but the magnetic field direction is not, I mean, how the magnetic field behave and what is the characteristics of the magnetic field is not the same as uh, electric field. So, however, the definition of flux, regardless whether it is electric field or magnetic field, it is the same, because it is still the flux density. So we call this the flux density. So we call this B is the flux density. So similar, comparable term is D, the electric flux density D. So now the magnetic flux density B is equals to mu naught, which is we call the permeability of free space, multiply the magnetic field intensity. So we call this the magnetic field intensity. So you should be aware by now. Comparable term, the magnetic field intensity is comparable to E, which is the electric field intensity. So while B, which the definition is called magnetic flux density, which is related to B, which is the symbol here is B. So the comparable term in electrostatic field, we call the electric flux density D. Okay, so so we write here for comparison purpose. So D, so this electric flux density. So this is electric field intensity. Okay, so they're comparable, but of course the behavior and the characteristics are totally different. Yeah. So the one is, you should already know, the source of magnetic field are coming from current source and also the magnet, while for electric field, the source are coming from charge, right? So however, when we talk about flux, so regardless whether it is electric field or magnetic field, is it is the surface integral, open surface integral. So the number of flux lines that passes through a surface. So we have, let's say we have a current here. So by now we should know how the magnetic field is evaluated using Ampere's law or by Savart law. So assuming that this is the current, a very long current. So by Ampere's law, we knew that this is the direction of the magnetic field, and this is basically the flux line. So if I define a surface like this, so this is a surface. Okay, so the number of flux line that passes through the surface. So then we calculate the magnetic flux. So of course, if we are dealing with magnetic field, then we call this the magnetic flux. If we're dealing with electric field, then this is called the electric flux. Okay, so one is in Weber. Okay, so another one is in what? Who can tell me? What is the uh what's the unit? So one is in Weber. So let me write this now. If in case you not sure, this is not equal. So this is, I should call this electric flux. So they are not comparable, yeah. Just for I mean they are not the same. Just for comparison purposes. So what is the unit for this, for electric flux? Anyone? So what is the unit? Anyone? T? No. Zenwei, you are close. So remember, the flux density, it is actually coulombs, or if it's electric field. So here is Newton per coulomb, right? So here is Newton per coulomb per meter square. So for flux density, that means Newton per coulomb meter square. If it's area, so you multiply area. So basically we get back what? Newton per coulomb, right? So that that is the dimension, right? That's the so that is the dimension for flux, electric flux. So however, if you say charge, then it's not correct. So unless it is a closed surface. So if it's a closed surface, then yes. So we will call it the charge enclosed. That means that is based on Gauss law. So if we define a closed surface, then we get the flux that through the closed surface is actually equals to the charge inside the surface. However, so in the magnetic field, the flux line is always form a closed loop and do not terminate on a magnetic charge. So I earlier in the chapter, I mentioned that there's no magnetic monopole like electric charge. We have a positive charge, we have a negative charge. So we call it mono because it's one, it's single. So there's no positive magnetic charge and there's no negative magnetic charge. There's no existence of this. So for a magnetic field, so if let's say you look at a magnet, so one come from the north pole, one come from the south pole. And do not think that, okay, if let's say I take a magnet, please do not think that I cut into this, then I have a north and you have a south. Then we have a monopole. No, 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 no. Please do not think like this, because if you break this, regardless how many times you break it, after you break this, let's say, there will be always a north and a south. There will be always. If you do not believe it, you buy one magnet, okay, a bar magnet, okay, try to break into half, and then one will become a north pole and one will become a south pole. You can try that on your own. And don't think that, okay, so if I don't break it into half, I will grind it. I will grind it become a powder form. Same. It won't. You won't get a monopole, regardless how you do it. You won't get monopole. Okay, so that's the uh, I mean, that's the nature of it. That's the nature of the magnet. So if let's say I use Gauss's law for magnetostatic field. So imagine now I have a closed surface. So this is an open surface. Let's say this is an open surface, like a handkerchief. So you place it you place it there, so open surface. So there will be a net flux if it's an open surface. There will be a net flux through the surface. If let's say this is an open surface, it's like a piece of paper. But if we define a closed surface like this, okay, so this is a closed surface. So whatever goes in, so you can see the flux line, whatever goes into the surface, whatever field, whatever magnetic field that passes through the closed surface. So you can see this is going into the surface, going into the closed surface, going into the closed surface. And here, out from the closed surface, out from the closed surface, out from the closed surface. So whatever goes in, so imagine you have a balloon like this, you have have a balloon like this. So whatever goes in comes out. So there is no net flux. There is no net flux. So therefore, when we apply Gauss' law for magnetostatic field, that means for the closed surface, the net flux equals to 0. And from here, we can apply divergence theorem. So we can apply divergence theorem, and divergence theorem will give us the divergence of magnetic field is equals to 0. So when we say divergence, the term divergence mean we are measuring how diverge the field is. But for magnetic field, if you look at how the behavior of the magnetic field is always circulating around, right? It's always circulating around, so it won't diverge like electric field. So if it's electric field, then the divergence is always out from positive charge, or negative charge is always in, right? So positive charge is always diverging, and negative charge is always converging. Okay. So therefore, this form the fourth Maxwell equation. So this form the fourth Maxwell equation. So far, we have how many of them now? So you have learned that you have learned the point form of this. So basically, we have learned how many of them? Cross E for electrostatic is equals to 0. And okay, so this is the 4 equation. So this is a 4 equation point form. In this is in point form. 4 Maxwell equation. Maxwell's equation for electrostatic and magnetostatic. So it's only applicable, this 4 equation, the result of this 4 equation is only applicable for electrostatic and magnetostatic. Okay, but if you really want to look into the generalized Maxwell equation, there's some modification for this equation. There's some modification for this equation as well as this equation. Okay, these two remain the same. These two remain the same. Okay, so only the curl product, will be some. There will be some changes only for the curl product. Okay, so let's look at one last example. So we have an infinitely long filamentary wire carries a current 2 ampere in the positive z direction. Calculate B. So what is the flux, magnetic flux at this point? So I want you to try this first before I write down my solution to you. So the current is in the z direction, 2 ampere. Okay. So you need to find what is the flux density at this point. And then subsequently, what is the this is the magnetic field, this is the magnetic flux density, yeah? Not flux, magnetic flux density at this point. And the flux through the square loop described by this limits, the radius limit, the height limit, and also where is the plane. Okay, I want you to try this first. Let's say try this in about 10 minutes. Yeah, 10 minutes. Okay, so for part A, so since it is a infinitely long filamentary wire, uh, carries 2 ampere in the positive z direction using Ampere's law. Um, so I don't have to write it again. So I will just write H equals to I divided by 2 pi R phi cap. Okay, so that is from Ampere's law. So I is 2 ampere. Sorry. So therefore B is mu naught I 2 pi R. Yep. So mu naught is 4 pi times 10 to the power of negative 7. The current is 2 ampere. 2 pi R. Okay. R is the radial direction, is the radial distance. Is the radial distance measure from the current element. Uh, that means the perpendicular distance from the current element to this point. So therefore, the perpendicular distance from this point is in the perpendicular direction from the current element. It is in the xy direction. So xy direction, and therefore r, it is square root of 3 squared plus 4 squared, which is 5. So 4 divided by 5 is 0.8 times 10 to the power of negative 7. So 80 times, 80, it is equals to 80 nanoweber. So that's part A. So now we have to go to part B, the flux through the square loop described by the surface. So we have to find the flux. So when we mention flux, uh, if it will be some calculation, I mean, it will be, the evaluation will not be 0 for magnetic flux. The evaluation will not be 0 if the surface, if the surface, it is an open surface, unless it's the closed surface. Yeah, but okay, let's look at the surface now. So from 2 to 6, okay, radial 2 to 6, and then the height is from 0 to 4 at a constant plane of 90 degrees. So constant plane of 90 degrees, it is from here to here. So this 90 degrees, right? So it means that the plane now, it will be like this. So from 2 to 6, from radius 2 to 6. So this is a constant plane. From then z is from 0 to 4, right? So this is the plane now. So that then we knew that because using Ampere's law, and we knew that the magnetic field, it is circulating around the current term, the current element. So it is circulating around the current element. So therefore, it will pass through this surface area. Then, and therefore, part B. for part B. So we have to evaluate the flux that passes through the area. So B we already found earlier, which is mu naught I divided by 2 pi r. Okay, this surface here is d rho dz, right? So the unit area, the differential area, the differential area should be written as dr dz, right? So this is dr dz. Okay, the normal direction to of the surface, the normal direction will be phi cap as well. So r is from 2 to 6, and then the height is from 0 to 4. So it's ln r 6 to z 0 to 4. So the value will be 4 pi times 10 to the power of negative 7 to 2 pi times ln 3 times 4, right? Okay. So 4 times 10 to the power of negative 7 times ln 3 times 4. So I have 1.7578 Weber times 10 to the power of negative 6 Weber. Right. Yeah, 1.756. Okay, it's there. So this 10 to the power of 6, then this is 1.7578 micro Weber. Yep. So that's the solution. Okay, so basically that's all for today. Okay, so we will continue with a new chapter tomorrow, but for today there's still plenty of time. So is there any section that you would like me to clarify further, or do you have any question to ask me? Okay, tutorial 4. Wait, tutorial 4. Yeah, okay, yeah. You can discuss this. Okay, wait. let's look at where do I get 4 pi r squared just now? The Ampere's law between B to R, between B to B plus T. Okay. So, so how do let's say, uh, ah, this is not 4, right? It's pi r squared, right? Sorry. There's no 4 here, I guess. Sorry. So there's no 4 here. Then this would be 2 pi r then. Yep. Yep. So there's no 4. Yep. Okay. Sorry, I just mixed up about the spherical and yeah, sorry. So it's supposed to be pi r squared. Yeah, correct. Okay, just to clarify a bit. So the area. So I'm just want to clarify the area is the area that enclose. So it's pi r squared, but there's a certain thickness, right? So there's a certain thickness. There's a certain thickness that between between the that I mean there's a certain thickness that enclosed by the Ampere's path. So for example, okay, I know my circle is not perfect. So let's say this is the thickness. So this is the Ampere's path, the Amperian path that enclose the surface area, right? So this path here. So it should be pi r squared. So evaluation from B to R. Yeah, B to R. Okay, Zenwei. So let's look at tutorial 4. We have some time. Okay, let's try. I'm not sure in 10 minutes time we can finish this. First, mm, okay, can anyone, okay, Zenwei, do you have, I mean, I do not want to do this from the scratch if possible because we only have 10 minutes. Can you give me the V expression and also the E expression? So E should be Q divided by 4 pi uh, 4 pi r squared, right? In the r cap direction. And V, if let's say, so V, I will say is Q over 4 pi R. Yep. 4 pi epsilon R, sorry. Okay, so this 4 pi epsilon naught R squared, yeah? So this is coming from this solid sphere, yeah? This solid sphere, there's a charge Q. So if, sorry, this R is not. So let's say, sorry, I would say R prime, okay, somewhere. So I would put a different R prime. So I so the charge density would be, let's say rho V, the charge density, rho V, it will be Q divided by 4 over 3 pi R cubed. So there's the charge density, right? Okay, so let's try to confirm this. Let's try to confirm this first, whether I did some correct. So rho is the charge density. So basically this is rho, yeah. So it is the volume charge density. So it's Q squared So dV, I would say dV is what? So I would say R prime square sine theta d theta d phi dr. Prime. But this is outside. I haven't evaluated inside here. But this is only for outside. This is only for outside, right? This is only for outside. So what about inside? I haven't. So I haven't do it for inside as well. So what is inside? So this is outside for V and E. So what is inside? So anyone can give me V and E inside? I think maybe we have to extend it to tomorrow, yeah. So let's evaluate. Let's evaluate inside first, yeah. So this is outside. I mean, if let's say by Ampere by Gauss law, okay, by Gauss law. So this is outside for maybe, so r squared r cap, let's say. So this is for r greater than r, yeah. So for inside, for r less than r, so charge enclosed will be q over 4 over 3 by r cubed, and this will be 4 over 3 by r cubed. So this is epsilon. So they never mention about epsilon, so I will just assume as epsilon. They never mention, they never really mention about the permittivity. So I will just assume as epsilon. So here is 4 pi r squared. So it's q r. Okay. So in the direction of r capped. So for v, so if let's say for v, therefore v, so from, so I need, so if let's say I want to evaluate, so from negative infinity, so from positive infinity to r, right? To a certain r value. So if for infinity, that means we have to use this term. The evaluation, we have to use this term. Okay. So one is, sorry, if infinity, we have to use this term. So infinity to r, infinity to capital R, and then, so infinity to capital R is this term, and then minus, then from R to R, so will be this term. So this part here, it will be Q over 4 pi epsilon naught R. And for this term is minus Q R squared over 8 pi epsilon naught R cubed R to R. Q R squared never mind. I will just do it mentally here. So this would be 3 over 8, yeah? And this would be Q R squared. Okay. All right. So we have, okay. Sorry, I think we need to continue this discussion. So so I will do it tomorrow. So tomorrow we will discuss this, yeah? We will discuss this question here. So we'll continue. All right? For tomorrow. All right, thank you everyone.